Hi again. So far we've been talking about the definition of the current. We understand a bit more what current is. We've learned a bit about voltage and electric potential, although we're going to learn a bit more about that today. But that leaves the resistance concept of resistance. What is it? How is it defined? What does it depend on? So we'll talk about this. First, what are the units? You know from high school the units are named ohms, and actually that comes from a proper name, the last name of Georg Simon Ohm, a German physicist who lived at the end of the 18th century, early 19th century. Okay, so you also know the symbol we use, which is the Greek capital omega. From mechanics, you probably remember lowercase omega that looks like a little W. That's a lowercase omega. This symbol here is capital omega in Greek. Okay, now before we go on, I want to make a few comments about the units. So we've learned about many different units, but it's important to keep in mind that actually everything that you've seen in mechanics or that you're seeing this semester in electricity, everything can be always expressed in terms of four fundamental units. The unit of mass, which is a kilogram, if we're in the Système International. So the mass unit, kilogram, time unit, the second, distance unit, the meter, and this semester we introduced charge unit, coulomb. So coulomb, meter, second, and kilogram. Everything that we're covering can be expressed in terms of those four units. So everything you've seen, including a volt, one ohm, and current, everything can be expressed in terms of those four basic units. For example, you already know that current is measured in ampere, and 1 ampere is actually 1 coulomb per second. You've seen that. Now, what about voltage or electric potential? You know that from what we've seen previously, that change of electric potential energy, delta U, is equal to Q times delta V. So delta V, voltage, is equal to a change of electric potential energy divided by Q. So you see that from this equation, 1 volt is equal to 1 joule per coulomb. So 1 volt is 1 joule per coulomb. Now, a joule is also can also be expressed in terms of those four fundamental units. So you probably remember from mechanics that 1 joule is just 1 kilogram meter square per second square. If you don't remember that, just think about kinetic energy. Kinetic energy is 1/2 mv square. So kinetic energy is in joules, and if you think about 1/2 mv square, you have a mass times the speed square. So 1 joule must be equal to 1 kilogram meter square per second square. So if you use this for 1 joule and you plug that in here for 1 joule, then 1 volt is equal to, so 1 joule is 1 kilogram meter square per second square. So 1 volt is 1 kilogram meter square per coulomb uh, times second square. Okay, so you see, this shows you that a volt can be expressed in terms of kilograms, meters, second, and coulomb. But of course, it would be a bit cumbersome to write all that here for 1 volt, so we switch to this shorthand. But a volt is expressed that way. What about resistance? But from R equal delta V over I, you know that therefore 1 ohm must be equal to 1 volt per ampere. So 1 ohm is 1 volt per ampere. Now we just said that 1 volt is 1 joule per coulomb. So if I use this for in here for 1 volt, then I get that 1 ohm is 1 joule second per coulomb square. Now, if I go back here and I say 1 joule is equal to this, and I plug that in this here for 1 joule, then I get that 1 ohm is 1 kilogram meter square per second square coulomb square. Okay, so I'm not saying that we're going to write things that way, because it's very cumbersome. But what's important is to keep in mind that you can always express a volt, energy, voltage, current, and resistance in terms of those four fundamental units. Okay, what's resistance? So this little cartoon expressed pretty well the relationship between the three things we're talking about. There's a voltage applied to charges in a circuit. We'll see in a second, or in the next video, that the voltage is related to a force applied to the charges. So large voltage applied, let's say a battery which is very strong applies a large voltage to a circuit. That means that the battery is pushing with a strong force on the charges. You have charges that are moving through your circuit, and they're measured. The flow of charges is measured in amperes, right? Coulombs per second. And resistance is something that makes it harder for the charges to move through the circuit. So this is a nice little cartoon. Pretty well summarizes what we're doing now. We're learning about now. Okay. Now, to be more specific, imagine you have a certain section of a wire like this, and you have a resistor here. Now, I just want to make one little comment. When we draw a circuit, let's say you draw a circuit, I won't draw the whole circuit, but let's say you have a wire, and then you have a resistor here that we draw like this, and then a wire here, and then it's connected to some other stuff, a battery, and so on. When we draw this, these sections here, we say these are ideal wires. We treat them as ideal wires. What we mean by an ideal wire is it would be a wire that will have no resistance. Now, in real life, there's no such thing except in very special cases. I'll talk about that in a second. But in all your experiments that we do in labs, these wires are not perfectly ideal. So every wire here has some resistance. But what we do is that when we do our calculations, we neglect the resistance of these wires here. Here you have a resistor, which is not a good conductor. It's like an insulator. So there's a large resistance here, but there's always a little bit of resistance in those wires. Now, what we mean by treating them as ideal wires is that we say, let's say this wire here has a resistance of 0.01 ohm. And this resistor here is, let's say, 1,000 ohms. So what we're saying really is that we assume that the resistance of these sections here, and here are negligible compared to that resistance here. So we neglect those resistance and we treat these sections as if they were ideal with no resistance. But of course, that's an approximation. There's always a little bit of resistance here. There's no resistance in a wire in a very special case when we have superconductors. And what happens is that certain materials, when you lower their temperature close to the absolute zero, they start acting as superconductors. That is, they have no resistance at all. But the only way to understand superconductors is to use quantum mechanics. So this is a bit beyond what we can cover this semester, so we won't discuss superconductors. If you want to learn more, read section 27.5 in the textbook about superconductors. But that's just for your personal knowledge. We're not going to discuss that in the lectures. Okay, so we made this approximation of neglecting the resistance of those sections here compared to those R here. Okay, so now, what we mean by the resistance of an element, you have something here, let's say like a resistor, okay, so you have this element here that is a resistor. You want to measure its resistance. How do you do that? You apply a delta V across the resistor and you measure the current. Then by definition, the resistance is given by the voltage you applied. Actually, there should be an absolute value here and here. Okay, the voltage you apply divided by the current gives you the resistance of this object here. Now we'll find out in the next video that the resistance here depends on the length of the section of, so I call that a resistor here for now, but that's any device, it's any type of object. So the length here and the resistance depends on the length, and also it will depend on the cross-sectional area. A here is the area of the cross-section. So you apply delta V here with a battery, let's say you apply 12 volts. You measure the current that flows here, and you do the ratio delta V absolute value divided by I, gives you the resistance of this object. Now, then what you can do, and we'll do that in the second lab, you can change delta V. You apply a different delta V now, and you measure the new current. You calculate again the resistance using the new delta V, again, really in absolute value. You change the delta V to a new value, I call that delta V2. You measure the new current, you do the ratio, you get R2. Now the key point is that for some elements, for some objects, no matter what delta V you apply, you get always the same R. Okay, the ratio always comes out to be the same. Those are special. There's other elements that if you apply different delta V, you can calculate a new R. You change delta V, you get a new current. You can always calculate this thing here. You get the value of R. But this new R might be different from the R before. Okay. So if we always get the same value of R, no matter what the delta V applied, okay, you apply new delta V, you get a new current. You do the ratio, you get R. Change delta V, get a new current, calculate the ratio again. If you always get the same R, we say the element is ohmic, in the sense that it obeys Ohm's law. So the resistance is well defined. It's always the same value no matter what delta V and I are. Okay. In that case, when you always get R to be the same, that means that delta V, for any value of delta V and I, you get the same ratio, then that means that delta V is proportional to I for that element. If you take a certain delta V, you get a certain I. If you double delta V, you get twice the current. If you triple delta V, you get 3 times the current. So those are for elements that are said to be ohmic, or they obey Ohm's law. And the setup is basically like this here. That's what we're going to do we're going to have in the lab. You're going to connect a some element here. You're going to measure the current flowing through it and the voltage across it, and you're going to measure delta V and I and do the ratio. Anyway, that would be the lab we'll do next week. Okay. Now, the next thing is okay. So if an element is ohmic, what happens when you look at you apply different delta V's, you get different current. If you plot the voltage, this is really delta V here. You plot the delta V and the current you get for each time, you get different points on this graph. If the element is ohmic, you get a straight line here. That just tells you that the delta V over I, the ratio is always the same value, no matter what I is, no matter what delta V is, the ratio delta V over I is always the same. Then you get a straight line. And on this graph, the slope of your line gives you the resistance. Okay. So in that case, so that's an ohmic component, the slope gives a resistance. If the component is not ohmic, the value of R is different for different delta V. You change delta V, you have a new current, you calculate delta V over I, you get a new value. In that case, when the component is not ohmic, the V versus I curve, or sometimes people would plot I versus V, doesn't matter. You don't get a straight line. You get something like this here. Okay, this is not ohmic. You can look at figure 27.7 in the textbook. That will show you 2 graphs, one of an ohmic component and one of a non-ohmic component. Okay. Now, the next thing we'll do is to actually get an equation for the resistance. How does it depend on L, A, and other parameters? We'll do that in the next video. Okay, so see you soon. Thank you.